The position of the celestial bodies that we observe from the Earth is constantly changing. It depends on the position of the observer on Earth and on the point in time at which the observation is made. Practical astronomy as a science reveals the relationship between these three components. If we know two of them, then we can always find the third. If we know the coordinates of the observer, we can calculate the positions of the known celestial bodies for any moment. Also, based on the position of the celestial bodies, we can find out the time. Celestial navigation, as a section of practical astronomy, solves the problem of finding the coordinates of the observer by the position of celestial bodies at a given time. The position of the celestial bodies in the place of observation is determined using a sextant, but it is impossible to get your coordinates directly from the readings of the sextant. The readings of the sextant must be linked to the time of observation. The relationship of the position of celestial bodies with the time of observation is carried out using a nautical almanac. The sextant readings and the nautical almanac data are the initial information for determining your position using special calculation tables. For celestial navigation, the sun can be used during daylight hours, and several dozen navigational stars can be used at night. For this purpose, I have compiled all the necessary tables, as in a nautical almanac. These tables contain information on the Sun and 21 navigational stars for the period 1939 to 1945. For celestial navigation, first of all, it is necessary to learn how to find and accurately determine the navigational stars. Let's start learning it right now. You can do it yourself with the free Stellarium program. Go to the official website of the program developer. Select the installation file that matches your operating system. Download and install the program. Launch it. This program is a virtual planetarium. You can specify the location from which you want to make observations. You can set the position by specifying any point on the map. You can also manually enter the coordinates. You can select the time zone. You can set the date and time of the observation in the selected time zone. By default, the program starts in real time. Using the control buttons, you can stop the flow of time. You can set the accelerated flow of time in both directions. Using a special button, you can switch to the current time. For the convenience of studying stars, I recommend setting up the program so that the sky with the stars is similar to what you see in the game. See how this can be done. Changes to settings must be saved, and to that you don't have to repeat the configuration the next time you start it. We will begin our journey in the northern sky. The starting constellation will be Big Dipper, which is easy to find in the sky. Then follow the arrows. They will lead us and point to the navigational stars. Cassiopeia is a good reference point for finding some stars. Let's continue studying the stars in another part of the sky. The starting constellation will be Orion. The position of celestial bodies in the sky is specified as follows. Imagine that you are on the bridge of the U-boat. You see the horizon around you. Now your gaze is turned in this direction. In this direction you observe a celestial body. The celestial body, the observer and the horizon plane form an angle that is the altitude, h. The altitude of the celestial bodies that we see above the horizon can take values from 0. In this case, the celestial body lies on the horizon. The maximum altitude of a celestial body is 90 degrees when it is at the zenith of the observer. In this case, the celestial body lies on a plumb line that passes through the observer and forms a right angle with the horizon plane. If we count the position of a celestial body not from the horizon but from a plumb line, then the celestial body and the plumb line form an angle called the zenith distance. The zenith distance of a celestial body that lies on the horizon is 90 degrees. The zenith distance of a celestial body at the zenith is 0. Altitude and zenith distance together make up an angle of 90 degrees. Having measured the altitude of a celestial body with the sextant, you can calculate its zenith distance. Along with altitude, zenith distance is a key parameter in celestial navigation. We will refer to it more than once. Another parameter of the position of celestial bodies is azimuth. In SH5, azimuth is distinguished as the angle between heading and direction to a celestial body. The angle between the direction to the north and the direction to the celestial body is called true azimuth. It is true azimuth that is of practical interest for celestial navigation. The SH5 sextant interface displays altitude, azimuth and true azimuth values when measuring. The U-boat position relative to the horizon is not constant. There is a difference between the U-boat horizontal plane and the horizon. This difference is a trim angle. It is important for celestial navigation to stabilize the horizon for altitude measurements. One way to stabilize is to dive to 8 meters. In this case, the U-boat has a stable trim angle of 17.1 arc minutes. If you are playing in a high realism, then you need to keep in mind that when the no stabilize view option is enabled, then SH5 sextant readings are counted from the U-boat horizontal plane, but not from the horizon. If you are measuring the altitude of a star whose azimuth is 0, add 17.1 arc minutes to the sextant reading. Do not confuse azimuth and true azimuth. Here we mean azimuth, which is the angle between your heading and the direction of the star. If the azimuth is 180 degrees, then subtract 17.1 arc minutes from the sextant reading. If the azimuth is 90 or 270 degrees, then the sextant readings correspond to the altitude of the star. It is not always convenient to select and adjust the position of the U-boat for altitude measurement. The best way to make celestial navigation comfortable is to disable the No Stabilized View option. In this case, the sextant readings will be counted from horizon and no corrections are required. Trim angle does not matter now. Measurements can be taken at any U-boat position. Before starting to learn the techniques of celestial navigation, it is necessary to clarify some details. This line is the geometric direction from the observer to the celestial body. In fact, light from the celestial body reaches the observer being refracted by the atmosphere. The altitude of a celestial body may appear larger than in reality by the amount of refraction. In SH5, atmospheric refraction is not implemented and celestial bodies are visible in accordance with the geometric direction on them. Refraction correction is not required. In astronomy, the relative position of space objects, the distance between them, and the direction from one space object to another are determined by the line connecting the centers of these space objects. The direction to the celestial body from the position of the observer differs from this line. The angle that makes up this difference is parallax. In order to enter the sextant readings into the calculation, you need to add the parallax value to them. The center of the Earth is the point on which the celestial and geographic coordinate systems are simultaneously based. The coordinates of a celestial body are determined by the line connecting the center of the Earth and the center of the celestial body. The observer's coordinates correspond to a plumb line that intersects the horizon plane at right angles. In celestial navigation, the coordinates of a celestial body and an observer are determined by angles, the vertex of which is the center of the Earth. The measured altitude of a celestial body is the angle whose vertex is the observer himself. In order to use the measured altitude in calculating the U-boat position, it must be corrected so that its vertex is at the center of the Earth. To do this, we will transfer the plane of our horizon so that it passes through the center of the Earth. The right angle to the plumb line must be maintained. The H2 angle corresponds to the corrected altitude. The difference between the corrected and the measured altitudes is the parallax value. The parallax value mainly depends on the distance to the celestial body. Consider a triangle that forms the parallax angle when observing the Sun. This side is formed by the radius of the Earth. This side is the distance from the Earth to the Sun. If you draw this triangle in accordance with the scale, then it will look like a straight line that connects the Sun and the Earth. The Earth itself, the center of the Earth, and an observer on the surface of the Earth will represent the same point. H1 and H2 angles now appear to be the same angle. The parallax of the Sun is non-zero, but still very small. In practice, the parallax of the Sun can be taken equal to 0. H1 and H2 angles in this case will represent the same angle, H. The stars are so far from Earth that parallax is considered 0 when observing stars. When observing stars and the Sun, we will consider parallax equal to 0. Since SH5 does not require correction for refraction and parallax, the altitude measured with the SH5 sextant can be taken directly into calculations. In the future, to explain the celestial navigation methods, we will need to place stars and an observer on the Earth's surface on the same drawing. It should be borne in mind that the relative position of a distant celestial body, an observer, and the center of the Earth cannot be shown on the correct scale. For example, we are conveniently drawing a star here, just to show the direction of the star from the center of the Earth. At the same time, we understand that the star should be located outside the field of our drawing. We also understand that the direction in which the observer sees the star corresponds to this line. These two lines are practically parallel to each other. They will intersect, having traveled tens of trillions of kilometers to the star. We know that the measured altitude corresponds to the angle whose vertex is the observer. But in order for the drawing to correctly show the relationship between the celestial coordinates of a celestial body and the geographic coordinates of the observer, it is necessary to draw the altitude of the celestial body relative to the center of the Earth. Since the sextant readings in SH5 do not need correction, we will directly draw the measured altitude relative to the center of the Earth. The zenith distance should also be drawn relative to the center of the Earth. Look at this arc of the Earth's surface. It corresponds to the zenith distance. This point is the projection of the star on the surface of the Earth. If we know the position of the projection of the star, then we can use it as a lighthouse when determining our position. You will soon learn how you can determine your latitude from the zenith distance of a navigational star. To determine the latitude, we need only one of the celestial coordinates of the star. Celestial coordinates are similar to geographic coordinates. An analog of geographical latitude is the declination of a celestial body. To understand this, it is enough to project a star onto the surface of the Earth. Let's connect the star to the center of the Earth using a line. The point of intersection of the line with the Earth's surface will be the projection of the star. The latitude of this point corresponds to an arc that runs from the equator along the meridian line. The projection latitude of the star and the declination of the star itself correspond to the same angle. Declination is the angle that is formed by the equatorial plane and the direction toward the star from the center of the Earth. Like latitude, declination can be northern or southern. The equator corresponds to 0 latitude and declination. North latitude and declination range from 0 to positive 90 degrees. South latitude and declination range from 0 to negative 90 degrees. The declination of stars changes insignificantly, and within a range of several years, the declination of the star can be considered constant. In SH5, the declination of navigational stars has a constant tabular value throughout the game. The values given in the table are valid for SH5 only. They differ slightly from the actual values. The main reason why stars change their position in the sky is the rotation of the Earth around its own axis. As the Earth rotates, the projection of the star traces a circle of latitude that corresponds to the declination of the star. In celestial navigation, it is accepted that we do not observe the stars themselves, but their images on the celestial sphere. The center of the celestial sphere coincides with the center of the Earth. The projection of the geographic North Pole on the celestial sphere is the North Celestial Pole. The South Pole projection is the South Celestial Pole. North Celestial Pole, North Pole, South Pole, South Celestial Pole lies on the same line, called the polar axis. The celestial sphere has a celestial equator. The geographic equator and the celestial equator lie in the same plane and have a common center. The celestial equator is the projection of the geographic equator onto the celestial sphere. Polar axis and equatorial plane form a right angle. A plumb line runs through the observer's position to the center of the Earth. The intersection of the plumb line with the celestial sphere is the zenith. The horizon plane passes through the observer's position and forms a right angle with the plumb line. An observer's meridian passes through the North Celestial Pole, South Celestial Pole, and the zenith. The observer's meridian arc between the celestial equator and zenith corresponds to the latitude of the observer. The dimensions of the Earth can be ignored in comparison with the distances to the Sun and to the stars. The dimensions of the celestial sphere are taken such that the Earth is a point. The Earth and the observer are the same point, which is located in the center of the celestial sphere. The horizon plane also passes through the center of the celestial sphere. The observer is located at the center of the celestial sphere and represents the common center for two coordinate systems. The horizontal coordinate system formed by the horizon and the plumb line, and the equatorial coordinate system formed by the polar axis and the celestial equator. The relative position of these two coordinate systems, namely the angles that they form with each other, are determined by your latitude. The inclination of the polar axis to the horizontal plane corresponds to the latitude. If you are in northern latitudes, then the north celestial pole is above the horizon and the south celestial pole is below the horizon. If you are in southern latitudes, the south celestial pole is above the horizon and the north celestial pole lies below the horizon. Polaris is notable for being located next to the north celestial pole. The proximity of Polaris to the north celestial pole can be used to roughly determine the latitude of the observer. The altitude of the north celestial pole exactly matches the latitude of the observer, so by measuring the altitude of Polaris, you can approximately determine the latitude of the observer. The error in determining the latitude by this method does not exceed 1 degree. This error is caused by the fact that Polaris, like other stars, changes its position in the sky as the Earth rotates. In celestial navigation, it is generally accepted that the change in the position of the stars is not associated with the rotation of the Earth, but it is caused by the rotation of the celestial sphere relative to the polar axis. The stars follow circular paths relative to the polar axis. The direction in which the apparent movement of the stars occurs corresponds to the direction of rotation of the celestial sphere. When looking at the sky for a short time, the stars appear motionless. Over time, you may find that the stars move counterclockwise relative to the north celestial pole. Looking in the direction of the south celestial pole, the stars appear to move clockwise. The circular path followed by the star corresponds to the declination of the star. The celestial sphere is divided by the horizon into 2 hemispheres. The hemisphere above the horizon is available for observation. The observer sees stars in those parts of the trajectory that pass above the horizon. Depending on the latitude of the observer, some stars are always above the horizon. Their entire path goes in the visible hemisphere. Other stars travel part of their path above the horizon. The other part of their path goes below the horizon. Some stars may not be visible at all because they never rise above the horizon at a particular latitude. Their entire path goes below the horizon. At the North Pole, the observer sees all stars that have a north declination. No northern stars set below the horizon. The entire northern sky is available for observation at the same time, while it is impossible to see the stars of southern declination. All stars in the south declination are always below the horizon. If the observer is at the South Pole, then he can simultaneously see all the stars in the south declination. The stars in the north declination are not available for observation. When in northern latitudes, the observer simultaneously sees most of the northern sky. Individual stars close enough to the north celestial pole do not set below the horizon at a particular latitude. A part of the southern sky is also available for observation, while some of the stars near the south celestial pole never rise above the horizon at this latitude. At southern latitudes, most of the southern sky and some of the northern sky are available for observation. Stars close enough to the south celestial pole do not set below the horizon at a particular latitude. Stars close enough to the north celestial pole never rise above the horizon at a particular latitude. When at the equator, equal parts of the northern and southern sky are visible. Absolutely all stars, half of their path follow above the horizon, and other half of their path the stars follow below the horizon. There are no stars in the sky above the equator that do not set below the horizon. It should be borne in mind that the position of the observer at the poles or at the equator is a special case. In the practice of celestial navigation, a more common case is when the observer is in northern or southern latitudes, when there is some inclination of the polar axis relative to the horizon, at which some of the stars are always above the horizon. The rest of the stars set below the horizon and rise above the horizon. The observer's meridian is divided by the zenith into northern and southern parts. If you are in the northern hemisphere, then this part of the observer's meridian crosses the horizon at the north cardinal point. This is the northern part of the observer's meridian. The southern part of the observer's meridian crosses the horizon at the south cardinal point. The stars rise above the horizon like the sun in the eastern part of the horizon. Reaching its maximum altitude above the horizon, the star is on the observer's meridian. After that, the altitude of the star decreases and it sets below the horizon in its western part. The highest point above the horizon in a star's path when the star crosses the observer's meridian is upper culmination. Stars that do not set below the horizon also have upper culmination. Note that these stars cross the observer's meridian twice. The second point of intersection is the lowest point of their path relative to the horizon and is the lower culmination. The stars that cross the observer's meridian in its northern part have zero true azimuth. True azimuth is 180 degrees if the star crosses the observer's meridian in its southern part. A similar movement of stars occurs relative to the observer who is located in southern latitudes. It doesn't matter which hemisphere, northern or southern, you are in. Upper culmination occurs when a star crosses that part of the observer's meridian. At the moment, the upper culmination latitude, declination and zenith distance are in the same plane. There are three general cases of upper culmination. This angle corresponds to your latitude. Declination in the first case, in the second case, in the third case. Zenith distance in the first case, in the second case, in the third case. In all three cases, latitude, declination and zenith distance are interconnected like A, B, C. If we know the declination of the star and the zenith distance during upper culmination, then we can calculate our latitude. First case. Second case. Third case. Let's consider the possible cases of upper culmination with specific examples. First case. You are in northern latitudes. The true azimuth of the star you see at upper culmination is 180 degrees. The observed star has a southern declination. The sum of declination and latitude in this case corresponds to the zenith distance. You can get your latitude from this expression. This formula also applies when you are in the southern hemisphere and observe a star with a northern declination and zero true azimuth. Second case. You are in northern latitudes. The true azimuth of the star you see at upper culmination is 180 degrees. The observed star has a northern declination. Latitude in this case corresponds to the sum of declination and zenith distance. This formula also applies when you are in the southern hemisphere and observe a star with southern declination and zero true azimuth. Third case. You are in northern latitudes. The true azimuth of the star you see at the moment of upper culmination is 0. The observed star has a northern declination. The sum of latitude and zenith distance corresponds to the declination of the star. You can get your latitude from this expression. This formula also applies when you are in the southern hemisphere and observe a star with southern declination when its true azimuth is 180 degrees. Thus, the three cases of upper culmination correspond to 6 different combinations of latitude, declination, and true azimuth. These formulas use absolute latitude and declination values without regard to their sign. If we apply signs to these formulas, then 2 formulas are enough to us. One formula is used when true azimuth is 0, another formula is used when true azimuth is 180 degrees. If the star does not set below the horizon at a given latitude, then its lower culmination can be observed. At the moment of lower culmination, it is also possible to determine the latitude of the observer. A similar formula is used for the southern and northern hemispheres. Lower culmination is rarely visible. More often than not, we will have to determine the latitude at the moment of upper culmination. For each specific latitude, there is a set of stars by which the observer can determine his latitude. First of all, it must be borne in mind that the SH5 sextant working range is limited to 75 degrees. As we agreed, the horizon plane passes through the center of the Earth. For clarity, we will leave the observer himself on the surface of the Earth. At the zenith, the observer has a blind spot within 15 degrees from the zenith. It is impossible to accurately measure the altitude of stars that are in the blind spot. It is impossible to accurately determine the latitude of the observer if upper culmination occurs in the blind spot. If the observer is located at the North Pole, then the southern hemisphere is not available to him for observation. He can observe only those stars that have a north declination. Polaris is in the blind spot in this case. If the observer is at 45 degrees north latitude, then he can observe Polaris at an altitude of about 45 degrees. Most of the northern sky is available for observation. On the southern side of the horizon, stars that have a southern declination are available for observation. Upper culmination of some stars takes place in the blind spot. You cannot use these stars to determine your latitude in this case. You can determine your latitude from other stars in the north declination and from some stars in the south declination. The names of the northern and southern stars are colored red here because the upper culmination of these stars occurs when the true azimuth of these stars is 180 degrees. To accurately calculate the latitude of the observer at the moment of upper culmination, this formula must be used. The formula must use positive sign for north declination and negative sign for south declination. Some of the navigational stars are not visible at this latitude. At the same time, note that the lower culmination of Alioth is available for observation at this latitude. You can calculate your latitude using this formula if you measure the altitude of Alioth at the time of lower culmination. If you are exactly on the equator, then at different times you can observe all the stars of the northern and southern hemispheres. However, in the blind spot there is an upper culmination of individual stars by which you can determine your latitude. For the rest of the stars, formulas are applied based on true azimuth. When using formulas, it is necessary to apply the sign that corresponds to the declination of the star. Note that no star's lower culmination can be seen at the equator. If you are in latitude 45 degrees south, you can observe the upper culmination of many northern stars and all southern stars. Upper culmination of individual southern stars happens in the blind spot. Some northern stars are not visible at this latitude. At the same time, lower culmination of some southern stars can be observed. To calculate latitude using this formula, you need to apply positive signs for south latitude and declination. In practical navigation, it is an exceptional situation when you absolutely do not know your coordinates. More often than not, you have an idea of where you are, and the purpose of celestial navigation is to refine and fix your position on the map. Knowing your approximate latitude, you can determine a list of stars by which you can refine your latitude. I have compiled a table by which you can find the stars to determine your latitude, at what azimuth their upper culmination occurs, and what formula you need to use to calculate your latitude. The last thing that we have to find out before we start determining latitude in practice at what time the upper culmination of a particular star occurs. During certain seasons, not all stars are visible at the time of upper culmination. I have compiled tables by which you can find the stars to determine the latitude in a particular season.